So here we'll be deriving the three kinematic equations. And that's something that you'll be using a lot if you continue on your career in physics. So first we need to start with dealing with acceleration. So acceleration will always be constant in these simple problems anyway, relatively simple. And acceleration will be equal to change in velocity over change in time. And what the triangles mean is just the change. So what this is really saying is the first velocity, the second velocity minus the first velocity over the second time minus the first time. And that's what the change in means. So you're taking your bigger, you're taking the bigger time subtracted from the smaller time, because time is always moving forward. But in the case of the velocity, you could start with a smaller velocity first, and with a bigger, that'll give you a positive change. Or you could start with a big velocity and with a small one, and that will give you a negative. Now that we know what acceleration is, we need to know what velocity is. And to do that, we first look at change in distance equals average velocity times change in time. And what this is saying is you're moving at some speed, and depending on how long you're moving for that speed, that's how much distance you're going to cover. So if you move stuff around, it'll be v equals change in x, change in distance, over change in t. And now that we have the basics, we'll move on to get the first equation. And we'll do that like this. So you're moving at some speed, at some velocity, and that's in meters per second. And we're going to add to that your acceleration and how long you've been accelerating for. So the acceleration will be in meters per second squared, and how long you've been accelerating for, we're going to multiply that by s, seconds. So meters per second is your velocity, plus meters per second squared, acceleration, times seconds, time. And because the seconds, one of the seconds in meters per second squared cancels with the other one, you're going to be left with meters per second plus meters per second. And you're going to be left with your final velocity. And so what this is saying is your start velocity, which will be noted by v null, or with a 0. It's your first one, so we start with the number 0, plus acceleration multiplied by time equals final velocity, or we'll keep it consistent. So that's the first equation. Big deal. And now we're going to move on to starting on the second equation. And to do that, we're going to have to look at the graph. So I guess change in time will be on the bottom, and change in velocity on the y-axis. And so what we're going to look at here is we're going to start at 0, 0, and as time increases, velocity is going to increase. And I'm just going to draw a very straight line. So its slope is 1, and so this is your line. Now, what we have to think about here is that displacement, so you're moving at some velocity, and it's taking you some time to do that. So the distance that you're moving is going to be equal to the area under the curve, which means that if you stop at some time, say at that time, we're going to draw that, and so the area here is going to be equal to your displacement, i.e. equal to the distance that you traveled. And so we know how to get the area of this shape, a triangle. We know this distance, and we know that distance. So it's going to be v times t times 1/2 for the area. So we'll write that down. One half v t equals displacement x. And so if we try and manipulate this further, we remember that acceleration equals change in v over change in t. And if we first manipulate the equation here, so it'll be equal to change in v equals change in t multiplied by a, and then we plug this v into that v. Well, this is supposed to be, well, this is equal to change in x equals 1/2 change in v change in t. They're equivalent. It's just easier to write it shorthand like this, because I know what I mean. But we'll plug this change in v into that or into that. It's really the same thing, but I'll keep it consistent with the triangles here. So we're going to be left with change in x equals 1/2 change in t multiplied by a times change in t. And we could clean this up, and it'll be equal to change in x equals 1/2 acceleration change in t squared. Because we have two of those, they'll multiply together, and we'll be left with that. And so this is the equation that you'll be using if you're starting at 0 velocity. You don't have a starting velocity, and so all you're worried about is your acceleration, how long, and the distance that you'll be traveling because of it. Now, if we want to throw in some kind of velocity, we could do that. What we're going to do here is look at change in x equals starting velocity multiplied by change in t. And we know that to be true. You have some velocity, you multiply it by how long you've been moving at that velocity, and that'll be the distance that you traveled. And now the equation I just erased was change in x equals 1/2 a change in time squared. And so if we plug those two in, plug this one into that one, we'll be left with change in x equals VO change in t plus 1/2 a change in t squared. So you put these two together, and the way we could do that is all of these delta x's are different. However, this one does not deal with a starting velocity, and in order to make this delta x account for this one also, so because these two are different, we wanna simply put them two together so we have an equation that has both acceleration and velocity. And the way we do that is we just add them together, and we're going to be left with a new delta x that's going to have both of these components, and all we need to do is add this with this, and we're left with this, the second kinematic equation. And now we're going to be working on the third and final kinematic equation. So to do that, we just have to quickly review that acceleration change in v over change in time. Change in time equals change in v over acceleration, and we bring those two down. That's very ugly. We bring those two down to have change in time equal to v final minus v initial over acceleration. And that's just what I explained in the beginning, where change in v is simply your final velocity minus your initial, and that's it. And now we also want to look at change in x is equal to the average velocity times change in t, and this is from the beginning. And we know that the average velocity is equal to the final velocity plus the initial velocity divided by 2, right? You have two values, and to get the average of those two values, you add them together, and then you divide by the number of values that you had, 2. So we have this, and we have that, and what we have here is these two values are here, and that's your change in x. So we want to plug in this for your change in t and this for your average velocity. And what are we going to be left with? We have change in x is equal to v final plus v initial divided by 2 multiplied by v final minus v initial divided by acceleration. Now, this is a little bit complicated. We're going to have to FOIL, but because VF, so if we multiply these two together, we're going to be left with VF squared, and if we multiply these two together, we're going to be left with V null squared. But when we do the outside terms, we're going to be left with negative VF times VO, and if we do the inside terms, you're going to be left with positive VF V null, and those two will cancel out. So change in x is equal to VF squared minus V null squared divided by 2a, and that is your final kinematic equation.